Section 4.3. In this section we will multiply radical expressions and we will add and subtract radical expressions. Recall that in order to simplify a radical expression containing variables with odd exponents, one must use the multiplication property of radicals. So let's just recall the multiplication property of radicals that we used in sections 4.1 and 4.2. If a and b are positive real numbers, then the square root of a times b is equal to the square root of a multiplied by the square root of b. So we'll be using that in this section as well. We're going to use the multiplication property of radicals to multiply radical expressions. For instance, the square root of 2 multiplied by the square root of 18 is equal to the square root of 36, which we know is just equal to 6. So this is the procedure that we're going to follow for multiplying radicals. First, we will multiply the radical expressions together. We will place the resulting product underneath one radical sign. Then, we will use what we learned in 4.1 and 4.2 to simplify the radical expression. So the first part of this section is multiplying radical expressions. So let's look at example A. The square root of 3 multiplied by the square root of 12 is equal to the square root of 36. And the square root of 36 is equal to 6. That one was fairly straightforward. B. The square root of 32 a to the second b to the fifth multiplied by the square root of 2ab to the seventh. So let's multiply this together and let's put the product underneath one radical sign. 32 times 2 is 64. A squared times a is a to the third, because remember when we multiply we add our exponents. And b to the fifth multiplied by b to the seventh is b to the 12th. And now we'll need to simplify this. Now recall, when we take the square root of a variable that has an exponent on it, we divide it by 12. But if you look at a to the third, it's an odd exponent, so remember we're going to have to split that up. So first of all, let's just split things up. We'll be taking the square root of 64, which won't be a problem because 64 is a perfect square. We're going to take one away from a cubed. We'll put the leftover underneath its own radical. b to the 12th is fine because 12 is even. We can divide it by 2. So let's simplify what we can. The square root of 64 is 8. The square root of a squared is a to the first. Square root a will just drop down. The square root of b to the 12th is b to the 6th. So keep in mind all of these are multiplied together. In future problems I probably won't put all the multiplication between them because we're just going to shove it all together. So the 8 and the a and the b to the 6th I will pull out front, multiplied by square root a. So 8a b to the 6th square roots of a. All right. Next one. All right. The square root of 18x to the 7th y to the 4th multiplied by the square root of 48x to the 9th y to the 5th equals the square root of 864 x to the 16th y to the 9th. Now, as you recall from 4.1, 864, we're going to have to do a factor tree for, okay? 2 times 432, it's a pretty long one. 2 times 216. 2 times 108. 2 goes into 108 54 times. And then we can go 2 times 27. 27 will break down to 3 times 9. And the 9 will break down to 3 times 3. And we're looking for pairs. Okay? So I'll put this across the bottom. We have 2 times 2 times 2 times 2. So there's a pair of 2's, a pair of 2's. We have a pair of 3's. And then you can see we have a leftover 2 and 3. I'll just stick those at the end. Okay, so this is a 4, 3 times 3 is 9, and your leftover 2 times 3 is 6. So that's how you have to split up the 864. Okay, now in future problems I probably won't do the entire factor tree since that lesson was from 4.1. Alright, so let's go ahead. We're going to rewrite radical 864 as radical 4 times radical 4 times radical 9 times radical 6 times radical x to the 16th. Y to the 9th, we can't divide that by 3, so we take 1 away. We'll write it as radical y to the 8th times radical y to the 1st. And now we'll simplify. The square root 4 is 2. The square root of 4 is 2. The square root of 9 is 3. Radical 6 is irrational. It drops down. The square root of x to the 16th. 16 divided by 2, remember, is 8. Take the square root sign off. The square root of y to the 8th is y to the 4th. And you'll drop down your radical y. So be careful when you're pulling things forward. It looks like we have 2 times 2 is 4, and 4 times 3 is 12. We have an x to the 8th and a y to the 4th. And then within the radical sign, we will have a 6 and a y. So 12x to the 8th, y to the 4th, times the square root of 6y. All right, let's multiply these two together. 6 times 24 is 144. A to the 3rd times a to the 5th is a to the 8th. B squared times b is b cubed. And c times c is c squared. We'll be taking the square root of 144. The square root of a to the 8th. We need to take 1 away from b cubed to make it even, and we'll put the 1 by itself here. And then we'll take the square root of c squared. The square root of 144 is 12. The square root of a to the 8th is a to the 4th. The square root of b squared is b to the 1st. We'll drop down radical b. The square root of c squared is c. So our answer will be 12 a to the 4th b c times the square root of b. All right, let's move on to adding and subtracting radical expressions. In order to add or subtract radical expressions, you must have like radicals. Two radical terms are said to be like radicals if they have the same index and the same radicand. The radicand is what you find underneath the radical sign. Okay, so for instance, if I have 2 square root 3 plus 4 square root 3, notice I have a radicand of 3 and another radicand of 3. So we would say that those are like radicals. So if I wanted to add these together, you're going to find we're going to be using the distributive property. I can read this as 2 square roots of 3 plus 4 square roots of 3. And it's kind of like saying 2 plus 4 square roots of 3. Kind of like pulling out that square root 3. So this would equal 6 square roots of 3. Now, within this class, we're only going to be dealing with square roots. So in other words, really when you deal with the square root, there's an implied 2 right here. And that's called the index. In future classes, for instance, you may take a cubed root, say, of 27, which would be equal to 3, because 3 multiplied by 3 multiplied by 3 is equal to 27. Okay, so let's just say I told you to add 3 square roots of 4 plus, or I'm sorry, if I told you to add the cubed root of 4 plus the square root of 4? Well, notice here our radicands are the same, but our indices or our index is different on each of these. This cubed root of 4 here has an index of 3. Right here, a square root of 4 has an actual index of 2. So you would not be able to add these two together, okay? Because they don't have the same index. But once again, the problems that we're doing in this section, you won't have to worry about what the index is because all of them will have an index of 2 because we're dealing with square roots. Okay, so you will just have to pay attention to the radicand or what's underneath the radical sign to make sure they're the same, and we'll try to make them the same by simplifying them. Okay? So let's just go ahead and look at these radicals here. The following are pairs of like radicals. Notice, look at the first example, 2x times the square root of 6 and 5x times the square root of 6. Notice they have the same radicand and they're both square roots. So if I wanted to add those together, 2x square roots of 6 plus 5x square roots of 6, just as an example, if I said 2x square root 6 plus 5x square root 6, I could think of it as being 2x plus 5x square roots of 6, which would equal 7x square roots of 6. Okay, so if I wanted to add those together, I could because they have the same radicand and the same index. You could do the same on the one below it. I won't bother to add those together because I've got fractions. These are both cubed roots, notice. We won't be dealing with cubed roots in this class. But also notice we have cubed roots of 17y. Our radicands are the same. So these are also like radicals. And now some examples of pairs that are not like radicals. 9 square roots of 3 and 9 cube roots of 3. Notice these have different indices. This first one has an index of 2. This has an index of 3. You would not be able to add those together. Down here we have 8ab square roots of 5 and ab square roots of 10. Although they both each have an index of 2, both square roots, they don't have the same radicands, so you wouldn't be able to add those together. So in order to add and subtract radicals, you have to have the same index and the same radicand. And the radicand is just a fancy word for what's underneath the radical sign. As I mentioned earlier, the distributive property is going to be used to simplify the sum or difference of radical expressions that have the same radicand. For instance, 5 square roots of 2 plus 3 square roots of 2 is equal to 5 plus 3 square roots of 2, which will equal 8 square roots of 2. Notice that radical expressions that are in simplest form and have different radicands cannot be simplified by the distributive property. If I have 2 square roots of 3 plus 4 square roots of 2, this cannot be simplified by the distributive property because the terms do not have like radicals. Notice the radicands are different. 2 square root 3 has a radicand of 3. 4 square root 2 has a radicand of 2. All right? Nothing we can do with that to simplify it. So this is the procedure for adding or subtracting radical expressions. Now remember, when we were multiplying, we could multiply the two terms together and then simplify once. When we're adding and subtracting radical expressions, we need to simplify each term first if it needs to be simplified. Then, if we have like radicals, we can use the distributive property to add or subtract as indicated. So that sometimes does make addition and subtraction of radicals a little bit more complicated than multiplication. Okay, so this first one we have 5 square roots of 2 minus 3 square roots of 2 plus 12 square roots of 2. So the first thing you should be glancing at is your radicands to make sure they're the same, which they are. So I'm just going to pull out. That means I'm going to have 5 minus 3 plus 12 square roots of 2. 5 minus 3 is 2, and 2 plus 12 is 14. So I have 14 square roots of 2. Let's look at the example next door to that. 3 square roots of 12 minus 5 square roots of 27. Well, this one's a little bit more complicated because notice my radicands are different. I have a radicand of 12 and a radicand of 27, so I'm going to have to simplify each of those sides first. Now, I'm not going to do the factor trees for these because I don't have much room. Well, I guess I can on a couple. I may not do it for all of them, though. But let me just come down here. If I do a factor tree for 12, I get 4 and 3. Okay, and you can see 4 is your perfect square, so I'm just going to stop there. That's how I will split up the 12. This 3 just drops down. So I'm going to have radical 4 multiplied by radical 3, and I'm just going to simplify that. That's going to be 3 multiplied by the square root of 4 is 2, multiplied by the square root of 3. 3 times 2 is 6, so that's 6 square roots of 3. Drop down that minus sign. Now, you can do a factor tree for 27. But think about it. We know that we're adding and subtracting, and we know that we want to have like radicands. So let me drop down this 5, and we're splitting up the 27. We know we would like one of them to be a 3, so that I'll have a like radicand. And I know 3 times 9 is 27, and that's nice because I can take the square root of 9. So 5 multiplied by the square root of 9, which is 3, multiplied by the square root of 3. 5 multiplied by 3 is 15. So I have 15 square roots of 3. So I have 6 square roots of 3 minus 15 square roots of 3. So 6 minus 15 square roots of 3. So that is equal to negative 9 square roots of 3. All right, let's move on. Three square roots of 2 plus the square root of 2 plus the square root of 2. Now keep in mind, this is 1 square root of 2 and this is 1 square root of 2. Okay, so really it's like 3 plus 1 square roots of 2, which is equal to 5 square roots of 2. 3 square roots of 2 plus 1 more plus another one would give you 5 square roots of 2. So we have 5 square roots of 2 there. Negative 3 square roots of 7 plus 2 square roots of 7. Negative 3 plus 2 square roots of 7. That's a negative 1 square root of 7. So I can just write my answer as negative square root 7. And these first ones are nice because our radicands are the same. And the page doesn't want to change. Bear with me and we'll see if it will. There we go. Negative 3 square roots of 11 minus 8 square roots of 11. So that's a negative 3 minus 8 square roots of 11. Negative 3 minus 8. Negative 3 and negative 8 is negative 11. So we get negative 11 square roots of 11. Two y square roots of 3 minus 9y square roots of 3. That's 2y minus 9y square roots of 3, which is equal to negative 7y square roots of 3. Square root of 45 plus the square root of 125, we're going to have to simplify each side of this. When I do a factor tree for 45 and I find my pairs, I realize my largest, I end up breaking this down to square root 9 multiplied by square root 5. The square root of 9 is 3, so I get 3 square roots of 5. So on this side, I know one of them has to be a 5. And I know that 5 times 25 is 125, so that works out nicely. The square root of 25 is 5. So I get 3 square roots of 5 plus 5 square roots of 5. That's 3 plus 5 square roots of 5, which equal 8 square roots of 5. Now when I did a factor tree for 128, the first thing I did was divide it by 2, and I got 64 and 2 as factors. 64 multiplied by 2 is 128, and 64 is a perfect square because 8 times 8 is 64. So I know right away that's the best way to split that up. But if you want to do your pairs or your factor tree and all your pairs, you can. This 4 just drops down, so I'm going to 4, and radical 128 is equal to radical 64 times radical 2. And I'll simplify that side. This is going to be 4 multiplied by 8 multiplied by radical 2, which equals 32 square roots of 2. Minus, I'm dropping down this 3. I know I want one of these to be a 2, so I have like radicals. 2 times 16 is 32, so I'm going to have 3 multiplied by the square root of 16 is 4, multiplied by the square root of 2. 3 times 4 is 12. So I have 32 square roots of 2 minus 12 square roots of 2. That's 32 minus 12 square roots of 2. That's 20 square roots of 2. Okay? So remember, with addition, you simplify each side. And then if you have like radicands, you can add or subtract as indicated. 3 square roots of 3x squared minus 5 square roots of 27x squared. Alright, so let's just look at this left-hand side first. I'm dropping down the 3 that's on the outside. Now, radical 3, you're not going to be able to do anything with that. And I'm going to take the square root of x squared. The square root of x squared is x. So I'm just going to write that as 3x square roots of 3. All you had to do was take the square root of x squared. You have a 5 here. 27, I'm going to rewrite it as radical 9 times radical 3. And I'm going to have a radical x squared to take the square root of. That's a 5 multiplied by 3. Radical 3 will stay there. The square root of x squared is x. Be sure to take the radical sign off that x. 5 times 3 is 15. I'm going to bring the x behind the 15 and then square root 3. So I have 3x square roots of 3 minus 15x square roots of 3. So 3x minus 15x square roots of 3, which equals negative 12x square roots of 3. All right, next problem. It doesn't want to let me go to the next problem. Boy, oh boy. Come on. I'll just give it a minute to see if it will correct itself. All right, it took me to h. Great. Okay. All right, in this last one, we have b squared times the square root of a to the fifth b plus 3a squared times the square root of ab to the fifth. So I'm going to drop down my b squared. A to the fifth, to take the square root of it, I need to take one away. And the leftover one, I'll put by itself. But the b, I'm not going to be able to take the square root of that either, so I'm just going to put it with the a. So let's simplify this. B squared, the square root of a to the fourth is a squared. And since a comes before b in the alphabet, I'll just write this as a squared b squared square roots of ab. And now let's simplify the other side. Drop down the 3a squared. Notice the square root of a, you can't do anything with that. The b to the fifth, you need to split it up. You'll have a leftover b. So you'll have a 3a squared. Drop down radical a. The square root of b to the fourth is b squared, and you'll have a radical b. So I have a 3a squared b squared times the square root of ab. So this a and this b I stuck underneath the radical. So you have a squared b squared plus 3a squared b squared square roots of a b. So a squared b squared plus 3a squared b squared, it's like there's a 1 there, is 4a squared b squared square roots of ab. All right, and that takes us to the u-tries. And so I will go ahead and stop there.